Hi everyone, welcome to class today. Oh, you know what? I forgot to open the chat. So let me open that real fast. How about chat? Here we go. Okay. So hope everybody's doing good today. So I got a couple of updates on terms of the schedule. So first of all, today we're going to be talking about those three algorithms that you see up there. As you will see, it's three algorithms, but the first two are almost the same, and the last one is more of an overview. We're not going to go too in depth into it, so we should be able to finish that in time. And then the next class that we have is going to be on Monday. Actually, you know what? No, we have. I keep thinking that we only have one day next week, but we have 2 days next week. So, yeah. So basically, next class, we're going to be looking at minimum spanning trees, and we will try and cover both minimum spanning tree algorithms in one day. If we don't, not to worry, we can always kind of bleed that off into the Wednesday. But either way, either finish talking about minimum spanning trees on Wednesday and start about Dijkstra's, or just go ahead and do Dijkstra on Wednesday the 24th. And that will pretty much wrap it up. So we have the 29th and the 1st free, unless, of course, it takes us more than one day for minimum spanning trees, in which case we can wrap up Dijkstra on the 29th Monday. Regardless, we will not be having class on December 1st, which is the Wednesday. I have to go get I got to do something basically, and instead, if you're as an optional class, I will leave a link to a lecture that I talk about P versus NP that I recorded a couple of semesters ago. That I like it because it covers not just P versus NP, but it covers a little bit about the other classes in the CS degree and some interesting stuff like Turing and automata and those kind of things. So that's gonna be the schedule. Okay, so we got 3 classes left after today, and then that optional class on Monday. That does mean, however, that no one's saying anything. I hope you guys are here. Let me check. Yeah, we have viewers. Okay, so yeah, someone just redeemed. Okay, cool. Yeah, so basically, that does mean that you should redeem your points for attendance not on the 1st, but on the 29th. Okay, so maximize your points. If you think you're going to get to the bigger tier, wait, otherwise you get the lower tiers, but that will be the last day. And I'll remind you as well, but just be aware of that. If you're for some reason you're not going to be able to be here on that day, then you might want to redeem before. And if you got the points already now, like others have, yeah, go ahead and redeem already. And just, if you get to the next one, then you'll be good. I will be making one lower tier than is available. So that would be, I think, so right now the tier is like 3,000 points or something like 1,500 points for a lower tier. So you can maximize your points that you get, but that will be the plan, okay? So again, today, these 3 algorithms, then next week, minimum spanning trees, and possibly Dijkstra. And if we don't finish Dijkstra on the 24th, then we finish it on the 29th. More than likely, we'll still have some spare time on the 29th, which we can use for potential review as well. Okay? You redeem your points, so you're good to go now. That does bring up a good point. There was one person whose name I think is like, or here, I have it actually. The Fox LOL. You did not contact me. I have no idea who you are, so you have to send me a message so that I know who you are so I can award you the points. So, yeah. Make sure you do that. And the other 2 that just did, make sure you also send me a message so that I know who you are. And make sure you list the 3 things: your name, your Twitch name, and the class, just in case that I don't get confused, okay? Can be email or message. But Steve, I already awarded your points because I remember who you were from last time. So you're okay. It's the people that have the names that are more like difficult, like the Fox LOL. That could be anybody, right? So, yeah. Okay. or tackle, like, 9.2K. You will make it, I think. I mean, yeah, you will make it. Depends if you attend every single day and whatnot. I did start the stream like the timer, so I guess that counts for the 15-minute bonus or whatever someone was mentioning. But okay, anyways, so that's the plan. So we got 5 algorithms in total to talk about before the end of the semester. We do 3 today, we do 2 next class, and then 1 the final class, and we still have 1 extra class as a spare to either finish or just do pure review, or probably more than likely finish and then do review for the rest. Okay, so yeah, all right. Okay, yeah, it's like I need to do anything, but no. Okay, so as a quick review, we talked about 2 ways of storing information. We said adjacency matrix and adjacency list. Adjacency list is useful when the graph is sparse, and adjacency matrix is when the graph is dense. And if you care about speed, adjacency matrix will always be better, but sometimes we might care about space too. And these graphs can get pretty big when you think about it. So I'd still recommend adjacency matrices regardless. Okay, so now that we've established all of these terminology, how to store a graph on a computer, how to represent the graph in general, we can move on to actually doing things with graphs. And so the first thing that we did when we worked with trees was looking at traversals to be able to kind of show the structure of the tree, right? To see like relationships and things like that. And also we could use traversals to build trees. We're not going to be trying to build a tree build a graph from traversals, because it's kind of weird. But what we are going to be doing is just our basic traversals. So with trees, we'd had pre-order traversal, in-order traversal, and post-order traversal. And then we also had level order traversal, right? So if you remember how those worked, they were kind of greedy, and when you coded them recursively, because really they try to go super deep on one specific side before they go try something else, right? So if you're doing like pre-order traversal, you're supposed to go to the node and then the left of the node and right of the node, right? So you're always going at the leftmost side of the tree, and only when you hit a leaf node do you go back and then try going the other side, right? And so that's kind of what we would call sort of recursive. And it turns out that type of traversals, whether it's pre-order, in-order, or post-order, they're all basically the same kind of traversal, which we call depth-first traversal, also known as depth-first search. Okay? On the other hand, we had one more traversal we talked about, which was the level order traversal, right? So in the level order traversal, we basically went by levels. And if you think about it, if we consider the root node the starting node of the traversal, the distance from the root node is how things are going to appear in the order of the level order traversal, right? So everything on this layer, which is a distance of 1 from the root node, is always going to appear first before this. And then anything beneath that is going to appear after all of this appears, right? So that level order traversal has a name with graphs, and it's called a breadth first search. Okay, now there's one catch with breadth first search versus level order. Breadth first search is just talking about the different layers or different distances from the starting point. But whereas with level order we were going like left or right consistently, with breadth first search there's no rule about that. So I could be like, well, this goes first and then this, and then maybe this goes here, here, and here, right? There's no order that says you have to go left to right or right to left. You can go in any order you want within that specific level, as long as everything within this level shows up before anything from the levels beneath it, right? So that's the only catch. So what I'm saying is, if this was like 1, 2, 3, 4, 5, 6, 8, and we did a level order traversal of this, we usually say it's just 5, 3, 2, 6, 5, 4, 8. But with the breadth first search, technically speaking, that is a valid breadth first search, but also doing 5, 2, 3, 6, 5, 4, 8 is also okay. The order doesn't matter within the levels. you could have any order. So that means that there's a ton of other combinations that you could have here, such as flipping these, right? Or flipping all of these, like that. So there's a lot of combinations here that you could have. They're all technically breadth first search, okay? And the reason why we don't think about left and right is because when you think about a graph, remember, like the way the graph is drawn doesn't matter. What you care about is how the thing is connected together, all the edges and all the vertices, okay? So now that we kind of got out of the way what depth first search is and breadth first search is, how do we algorithmically figure out a traversal for a graph? Well, there isn't a root node per se in a graph, and there's not really a leaf node in that concept. What we say is we have to pick a starting point. So whenever you're trying to do a traversal in a graph, you have to pick a vertex as a starting point. And it can be whatever you want, but you got to make sure that you establish, like, this is my starting point. Or if I ask you, do a traversal on this point, then you know, right? You can't just standardize and assume that everybody's going to pick the same starting node because it's a graph. So there's no top and bottom, there's no left and right. It's just a thing that exists and they can move around basically. So once we establish that, then yes, you can go ahead and algorithmically figure out what the level order traversal is, or breadth first search, or what these recursive traversals like depth first search would be. Okay, so if you code the graph with pointers, then it's very easy to do the depth first search traversal, because all you got to do is write a function that basically tries to go to all of the edges going out of a graph, right? And just call the function with that. And then if it gets to that edge and there's more edges, it goes in. And once it runs out of places to go, then you can just basically return and it goes back to the previous call, right? There's one catch about doing that, and that's when you have a potential cycle in a graph. So if I have an undirected graph, where basically any graph of that would be a cycle, suppose that I have something like this, and suppose that I decide this to be my starting point. With a depth first search traversal, you just basically keep going as deep as you can. So like maybe you go here, and then when you get there, you run out of places to go because you came in from here. So then you go back, and then from here, here's the thing. You don't want to go back this way and come back up, like go this way, because you already been there. So you have to have some form of memory to remember where you visited, to avoid like going on forever, because you could potentially just keep going in circles here, thinking it's a new path or a new edge that you're visiting, but you've already seen these edges, right? So when you're coding this, you have to have a way of keeping track of that. And it turns out that you can use a stack or a queue to very easily remember that kind of thing. And so when you do that, then you know that you still haven't visited this spot. So then you go here, and then you have nowhere else to go, so you're done. So coding this is not hard. And when you're doing the like adjacency matrix version of this, it can get a little tricky, but you just have to look at the horizontals or the verticals in the adjacency matrix, or just look at the horizontals within the adjacency list. Okay? If it goes in a loop like you illustrated, would encode it be a continuous loop or a segmentation fault? No, so you don't want it to go in the first place, because otherwise it'll just go for infinity, and then if it's a loop, it'll just run for infinity, or if it's recursive, it's just going to eventually run out of memory. So what you need to do is a way of remembering, I've already visited this edge, or I've already visited this vertex better, and be like, I don't need to visit again. And that's the other thing. When you're doing traversals, you don't necessarily care about visiting all of the edges. You only care about visiting all of the vertices. Now, this is something that does not apply when we're talking about trees, because there's only basically one edge connecting each node of a tree, right? There was never a tree that had two edges coming into it. Now, you might be thinking, well, what about like a parent and two children? Well, yes, but I'm saying from the beginning of the tree, which is the root, going down, there wasn't a way that you could ever come back into a node, or that you would have two edges that would arrive you to a node. And so this wasn't a particular problem there or something to think about. But when it comes to just a generic depth first search or breadth first search, you care about visiting all of the vertices, even if you don't necessarily go through all of the edges. Okay? So we're going to keep track of what vertices we visited. And of course, we need to know how many vertices there are so that we know when to finish. or if there is just no other way to get there. Because here's the thing, technically speaking, I know you've seen all the graphs that I've shown you are things that are like connected, right? Like this is just a graph. But you know what's also a graph? This is a graph too. Like this whole thing combined together is a graph, right? And so this graph is not necessarily connected. Like there's two sort of clusters of vertices connected, but we still consider the whole thing to be a graph. And so if you start a breadth first search or depth first search here, you're only going to be able to visit that and nothing else, right? And then if you start here, you're going to be able to visit all of this, but you're not going to particularly visit the top ones, okay? So, you know, when you're doing that, just be aware of that you may not necessarily visit all vertices when you're trying to do these traversals because there may not be a path there. It's like, imagine the road is closed and you just can't get there, okay? All right, so now that I've established all of that, let's just figure out how we can actually do this. So I'm gonna go ahead and bring in a graph, or just draw a graph in, and we're gonna start with breadth first search, okay? Because that one's the harder to do, so I wanna spend more time on that one. And hard, really not hard, but here's the thing. Once you see this, you're gonna be like, darn, I wish we would have done this when we were doing the level order traversal in trees, because you can use the same algorithm with your trees, and it would have made it easier. And maybe some of you have looked it up at some point and saw this, so this might not be the first time you see this, which is fine. All right, so breadth, wait, that's not how you spell it. I think this is how you spell it. Okay, and so I am going to go ahead and pick an example that I know is going to work, just so I don't accidentally make a mistake. This looks weird. Let's make this one longer so I can do it. There we go. Like that, okay? So this is a undirected, unweighted graph, or also known as an unordered, unweighted graph, which means that there are cycles by, you know, because it's undirected, so there's always cycles. Okay, so we have our graph and we need to pick a starting point. So I conveniently named our starting point S, okay? So that is going to be the start, S for start. And we want to perform a breadth first search. Now, before I go ahead and continue, I'm going to copy this and just paste it like way down here, so that I can use it to then show you the same graph, but with a depth first search, okay? So there's a couple of things that you need to do to be able to achieve this algorithm. So as I said, you need to be able to remember what you have visited and what you have not visited yet, okay? And so for that, you are just going to go ahead and make a little array. And we're going to call that array sort of the visited array, okay? Now, there is an assumption being made about this, and that is that you know, because you have some sort of adjacency matrix, all of the vertices that exist in your graph. If you don't have that piece of information, it's not the end of the world. You can build this array as you visit things. So, why is it not making a square? There we go. So either one's going to work, okay? In fact, I can do that. I can just go ahead and put that in and build that in as I make it. So, however, I'm going to cheat ahead and just kind of put the right number of squares here so that once we do add things in, it'll be okay. So is that enough? A, B, C, D, E, F, G, H. One more for our S. Okay? I am going to throw in S because that's where I'm starting. So by default, I have already visited that. Okay, so this array is going to be something that you're going to build as you see nodes, so you remember that you've seen them before. Okay, you have to, otherwise you go for infinity because you have like amnesia. So you're walking the same path every day because you don't know you already walked it. Okay, so the next thing or data structure that you need to keep track of, I'm going to shrink this a little bit, is for a breadth first search algorithm, you want to have a queue. So hello queues, long time no see, since what, it's been like 2 months since I saw you last queue. Oh, we saw the heaps, right? Those were kind of queues. Could you do this with a heap? Yeah, don't do it. I mean, I think you can, but because it is a priority queue, you just make sure you don't do weird priorities, but it's like overkill. Okay? Yes, you could in theory use a hash table for the visited array, but I don't know if you get much benefit from that. Only if the nodes have a hard, like if you don't, let's say the nodes, it's convenient there are letters here because that translates to numbers. But if the nodes were like, you had a billion different nodes and they didn't have a unique identifier, yeah, I guess you could use hashing for that. But let's not get that fancy with that. Okay, so we're gonna have a queue. And that's it. Those are the two main data structures that you need, and also, I suppose, somewhere to keep your output. Because this is a traversal, and those traversals are going to get us output, right? So the letters in the specific order. The first output is going to be the starting of the node, or the starting of the point, just like with a tree traversal is the root. Actually, technically speaking, with the trees, it's not always the root, right? Because like if you do like a post order traversal, then technically speaking, the last item of the print is the root. So therein lies the small difference. Whether you do depth first search or breadth first search, you always print out the root. So it's more like a pre-order traversal when you're thinking about depth first search than it is the other two. But you can still think of the two in the same way, because you could modify this if you wanted to make it that way too. Okay, so just think more like pre-order. All right, so before I go any further, let me show you the rules that you want to follow when you're going to do this. Okay, so whenever you visit a node, the first thing you want to do is you want to mark it as visited, aka set this Boolean array that you have here, because it's a little Boolean array for optimization purposes, set that to true, and add it in if it's not there present. Okay, so in addition to that, you also want to add to your output whatever vertex you're at, because you're just visiting it. And then finally, you want to add to the queue all adjacent nodes that are not visited. Okay? So you want to do that. So to make sure that you understand, I am going to go basically through the entire thing, but whenever you start, you're going to add this starting node to your queue, and then every time that you move on, you're going to keep removing something from your queue, and you're going to run through these different series of steps, which are mark it as visited, add to output, add to the queue for adjacent nodes that are not visited, and so on. There's one more thing that I didn't put here that you should do at the top, and that is you only are going to be doing all of these things if what you're looking at has not been marked as visited yet. So if not visited, okay? So let's run through it, then we can ask questions and whatnot. So step one is I am going to throw into my queue the node that I need to start with, okay? So I'm gonna go ahead and put S to start. All right, so now I can go ahead and say, if not visited. So for the first time, it's not visited, technically we just start out. So we have this sort of system where everything is empty, and we have S right here. Okay, so we take out S from the queue, and then we say it's visited. Sure, we add it to the output. So that's step two. So let's add it to the output, and then add to the queue all adjacent nodes that are not visited. So in this case, we have A, C, and G. Has A been visited? Well, it's not even in our visited array yet because we didn't know it existed. So let's just add that in. And then similarly with C and G, they're not here, right? Yet. So again, I want to keep this alphabetical to make it nice, but you would just add them in the order that you find them, right? So we can add C there, and then we can add G, which here is going to be B, C, D, E, F, G. I think I added one too many. A, B, C, D, E, F, G, H. Oh, I added one too many boxes. Whatever. Let's just put them on the order we see them. We'll make it more authentic. I'm sure we won't mess up the algorithm. Famous last words. So we see A, or sorry, we start with S. And then we put all the adjacent nodes. So they're A, C, and G. How many nodes should be here is how many edges are coming out, right? So we got A, C, and G. So that's it. By the way, this algorithm, I'm only really going to show it to you today with the non-directed version. But with directed, it's the exact same thing. It's just you don't consider all edges to be outgoing. You only take the ones that are actually outgoing, and so on. Okay? So because A, C, and G are not visited, we're going to be adding them to that visited array. And we got to make sure we mark S as visited. So in addition to that we add them to the visited array, we got to add them to the queue because they're not visited. So the ordering doesn't matter here. So I could add them as ACG, I could add them as GCA, whatever. The order is what you're looking at. So you probably have a list of pointers and you're just going through each pointer. Or if you're looking at your adjacency matrix for this, if we were looking at that row for the adjacency matrix for S, it would probably be something like this. It would be an S here from the from side, and then here there'd be like an A, B, C, D, E, and so on. And then all of these would be basically 0 with the exception of that one having a 1, 0, 1, and then all zeros here until we get to the G where there'll be a 1, right? So you would be looking at this horizontal line to identify which of these to add, okay? So that's what it would look like from an adjacency matrix implementation. But again, we already talked about that, so I kind of assumed that you'll figure that out. And if not, when you're coding these algorithms, you'll figure out those little, technicalities. Okay, so we added them all to the queue and we are good to go. We're done with this node. So the next thing we need to do is we need to dequeue. And the way we're going to know we actually finished the algorithm is when the queue is empty, okay? So what is the next thing in the queue? Since this is a queue, we should probably list something as the front and the back. So we'll say the front is there and the back is here. And our queue is very unoptimized because I don't feel like wrapping things around. So we'll just kind of erase them as they go and keep adding. Okay. So let's go ahead and dequeue the next thing. So we take out the A. All right. So first we check if the A has been visited. The A has not been visited because there is an A in our list, but it's not marked as visited. So we go ahead and mark it as visited now. All right, marked it as visited. Next thing we do is we have to add it to our output. So go ahead and throw it in our output. Very cool. And finally, we need to add to the queue all the adjacent nodes that are marked as not visited. So A has 2 adjacent nodes, B and S. B is not in our visited array. So we're going to add it there and we're going to throw it into the queue at the back of the queue. And then S is connected to it as well. But S is already marked as visited, as you can see right there. So because it's already marked as visited, we don't need to add it to the queue. And we don't need to do anything to the visited array because it's marked, okay? So the only one that gets added is B, okay? This is where that memory concept comes in, so you're not going in circles forever. Very cool. Next thing, let's take out the C. Has C been visited? No, it has not. So let's go ahead and mark it as visited by putting a 1 there. And then, and of course, initialize everything else to 0. I'm not putting 0 because I got to erase it afterwards. But yeah, that way 0 is unvisited. And so, yeah. So mark as visited, add to output. So we're going to put it into our output there. And then we're going to add all neighboring nodes that are not visited. So C has a lot of neighbors here, adjacent nodes. It's got 4 of them. It's got this, 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 and this, right? So let's go one by one. Again, the order doesn't really matter here. By the way, when you're coding it, you do have a pick an order. So just go in whatever order they're listed in your list of. You probably have an array of pointers, or again, you're looking at an adjacency matrix horizontally. Okay. I have a reminder. Sorry, I had a reminder that I have a meeting tomorrow, so I'm going to UNLV tomorrow. So for some reason, I guess I put an alarm the day before. Okay, so yeah. Okay, so let's go ahead and just go in whatever order. So I feel like going in the order of counterclockwise for this one. So I'm going to go with S first. Well, S has already been marked as visited, so we're not going to add it to the queue. All right, that takes care of that one. Next, F. F is not even in our visited array, so we're going to add it in. And then we're also going to add it to the queue. Then we got E. So we're going to throw an E in there. And then we got D. So we're going to throw D in there as well. None of these have been added to the... Oh, I'll put that in there. Okay. So, darn, I should have gone in the same... See, now I went in a different order than my example. The reason why I wanted to go in a specific order was to show you some interesting cases, but it's okay. We'll run into them probably anyways. Okay. Yeah, okay. Yeah, I just see it. We are still going to run into the same case, so that's good. All right. So, yeah, we added them all. So we only added 3 of them because the S has already been visited, so we're good to go. Do not forget to mark whatever you just went through as visited, which we did. We have a 1 there. As a good way of verifying that you didn't forget, like on a test, is like the number of letters in your output should be the same number as the ones you've marked as visited. So that's a little tip for you for your testing purposes. All right, let's move our queue down a little bit. It's getting up a little bit. So there we go. All right, so next thing to come out is going to be the G. So hello G, have you been visited? Nope. So then in that case, go ahead and add it to the output. And then add all adjacent nodes. Oh, mark as visited. Don't skip the steps. It's very easy to make a mistake if you skip steps. For computers, it's easier. For us, we can get into this ubiquity that basically makes you miss things because you're so used to it. Okay, so mark as visited. Add to output. Okay, add the adjacent node. So we got 3 adjacent nodes. We got S, F, and H. S is marked as visited. And then F and G are not marked as visited, so we are going to go ahead and add them in. As you notice, and this is what I was trying to hope that would happen, is that you have 2 G's in the queue already. That's okay. That's not going to be a problem because of our visited array. So that's kind of what I was hoping would happen. So I'm glad it has happened. Just because, people panic. If they don't know that you can do that. You're like, oh no, there's 2 F's. Does this mean I broke it? No, you didn't break it. It's a feature, not a bug. Okay, so yep, we're good. Let's take the next thing out. We got a B out. And by the way, well, let's do the B and then I'll come back to that. So mark as visited, add to the output, which we just did, and then add all adjacent nodes to B. Notice with the B that the only adjacent node is A, and that is already visited, so we're good to go. So, all right. Now, let's go to what I was going to say. We know, in fact, before we do the algorithm, we should know what the answer to this is, because this is the starting node, and so all the nodes that are 1 away from it, which are A, C, and G, should show up before any of the nodes or vertices that are 2 away from it, such as B, D, E, F, and even H. Those are all distance of 2 away, right? Yeah. So as you can see, the algorithm is working because it did put these 3 before it put the V. So that's a good sign for us, okay? And of course, that's a good way you can verify in your test. Should you add to the array? Should you add H to the array when you visit G? Oh yeah, I didn't add it, did I? My bad. When did I visit G? Let's see. I just visited before this, so A added nothing to it. So then I am going to. Oh, I think it's because I added G. I didn't mean to add G, right? Because I was at G. I meant to add H. That was the mistake I did. I meant to add F and H. So, yeah. So I think, yeah, when I got to G, you were supposed to add S, F, and H, but S is already visited, so you just add F and H. So I added F and G for some reason. So good catch. These are very meticulous and repetitive algorithms. As you see, it's very easy to make a mistake. So you have to be very, very careful with this stuff. Interestingly enough, that wouldn't have broken this in this specific graph, but it could have broken it in other scenarios. So we would have gotten lucky, but you may not get so lucky in the test or something. So yeah, play it safe. Like I said, you could do it ahead of time like I just did and know that I should get A, C, and G before B, D, E, F, and H. And after that, it doesn't really matter as long as you get all the letters in. So yeah, okay. I'm going to run out of space. Let me move my Q down a little bit, just so that I have space for the output. Okay, so here we go. I'm wondering if I was gonna say, like, I don't like the fact that I have these two black bars here, but if I zoom in, then you can't see the graph, so it bothers me. I guess I should redesign this to be more horizontal. We'll do that for the second, for the DFS version. Okay. So yeah. All right. So next, let's take out the next letter. So we're gonna take out, take out F. F is not visited, so we can mark it as visited before we forget. Then we add to the output. So just make sure we're very meticulous about this. And then get all the adjacent nodes. So F has two adjacent nodes, C and G. C is visited, G is also visited. So we don't need to add anything actually for F. Cool. All right, nice. We're done with that one. E, mark as visited before I forget. Also, I'll add H here and that because I should have added at some point because we did see that. That's okay. E has been marked as visited now. We can add to the output and then add adjacent nodes to that. That's C and H. C is already marked as visited, but H is not, so we're going to add it in. Okay? That's okay again. There's two H's, not a problem. All right? So get the next one out. Mark as visited. Add to the output. Add adjacent nodes. D only has one, which is C, but C is already marked as visited, so don't need to do anything there. All right, we're down to the last three here. But doesn't mean we're done, because I mean, these could add even more things in there. All right, so let's take out F. So when we take out F, F is already marked as visited, so we don't need to do anything up here. We just discard it. Take out H. H is not marked as visited, so we can mark it as visited, and then we can add it to the output, and then add neighbors that have not been visited. In this case, H has two neighbors, G and E, but they're both marked as visited, so we don't need to do anything. Finally, we take out the H here, which in this case, it's already been visited, so we just throw it away. And then we take out the next thing from the queue. I have a segmentation fault because we forgot to like, you know, check whether it's empty before calling the queue right now. What we do is we try to get something out from the queue. We see that it's empty, and that's how we know. We put that little if statement there. If queue size is equal to 0, you know, return that you're actually done or something. So we're done. So this is our traversal. Congratulations. All right. As you can see, things did print out in the right order. However, there is more than one depth first search traversal for this graph. In fact, there's a lot of them, because I mean, like the B and F could be flipped and you'd be good to go. How would we get the other one? Well, every time that you made a decision between adding, like every time that you hit a node, a vertex, and you were adding adjacent matrices to that, or adjacent vertices to that. So for example, when we got to C, we added D, E, and F. We didn't add S at that point because S was already there, but we did add D, E, and F, and I just added them in whatever order I wanted. In fact, I think I said counterclockwise, right? That order that you add things in would, if you every time you add them in a different order, may give you a different solution. Okay? This is a pain, by the way, for the grader to figure out if your traversals are good or not. So I kindly ask you, it's not required, but I kindly ask you to ease the grader's pain. And when it comes to tests, I will either give you letters or numbers for these kind of problems. I ask you to do things in an alphabetical manner. So like in this case, always add D first and then E and then F. Because then the TA only, like, you know, all of your submissions will be the same. We're not going to think you're cheating because you all added it alphabetically. And then they can actually like grade it faster. Otherwise, if every single one of you chose a different way of doing this, then they have to grade like essentially 20 different versions of this. And as you saw, it takes a while to make sure that the order of everything is nice. So it's not nice. So be nice to your graders. I mean, they'll grade it anyways, but don't you want them to be smiling when they grade your test? Be like, oh, you know, let's give them some points, partial credit for this or that, versus like, oh, no. You know? So, yeah. Okay. So that's the algorithm. Like I said, this is like one of those algorithms that you might be like, well, I could have done this just by eyesight, looking at the graph. And that is true for this graph, but imagine a graph with a billion nodes. It would take a long time to do. Algorithmically, once you code this, you know, it's done like that. So in terms of time complexity, this does take a while because you have to visit potentially every single edge in like a worst case scenario, but that's still not bad, you know, all things considered. Okay, so now I'm going to go ahead and do the depth first search version of this. And it's literally going to be the exact same algorithm, but instead of a queue, you have a stack. And that's it. That's all there's to it. So I'm going to try, I'm not saying it'll work, but I'm going to try to do it faster. But as you see, it's very easy to make a mistake. Although what I want to do this time is I want to make it horizontal. So we're going to see if I can achieve that. Okay, so there's my rule set. I am going to copy pretty much everything else. Yeah, look at that. We should have done that before. We're just like, at least me, I'm so used to like a paper. Papers are very, you know, I mean, landscape versus portrait. So we're used to doing things in portrait mode, but I think for the video, landscape works better. So. It's like, look at that. So much nicer now. Okay, and we also want to reset this thing. Oh, okay. All right. Same rules as before, except replace the word queue with stack here. And of course, replace the word queue with stack here. And the word top. Top is going to be like that. So it's going to be like a bucket. All right. So yeah, let's go ahead and start it. So look at that. It looks nicer already, the fact that we're doing it that way. I think we can probably make this even bigger too. All right. So again, when we're doing the depth first search, we do need to pick a starting point. So again, we're just going to start with the same one. And also in the test, that's another thing. We're going to give you a starting point because like otherwise that's even more combinations of traversals. Like this graph could have hundreds probably of traversals depending on where you start off with. So, because I mean, let's see, each one has, at least for the breadth first search, like you could have these 9 and then you could also have those, 16. Yeah, so it's over 100 like different different combinations that the TA would have to potentially look at. So yeah, okay. So yeah, all right. Starting point. So we start. We're gonna add as a starter the S to the Q where we want to start, and then bam, we let the algorithm run. So let's get onto it. So we are going to pop from the stack. And of course, we don't have that in the visited array, so we're going to add it. And then we're going to mark it as visited. And then go ahead and add it to the output. And then add all of the neighboring nodes to the stack. Okay, so we got A, C, and G. Again, depending on the order that we add these in, it's actually going to be a different, a completely different, basically depth first search traversal. Okay, so in this case, I am going to go ahead and add in. I'm just going to add them in alphabetically this time. So A goes in first, and then we get C, and then we get G. And we're only adding the ones, remember, that are not visited, okay? And none of these are visited. So since they're not visited, we can't, but we know they exist. We can add them to the top of this, but leave that at 0 because they're not visited. I'll leave it blank because we don't have to erase everything. Okay, all right. So then same as all, but don't take out from the bottom because it's a stack. Take out from the top. So we take out the G. Has G been visited? No, it has not. So add it to the output. Mark it as visited. And then add neighboring nodes to the stack that are not visited. So in this case, we have S, F, and H. S is marked as visited. F and H are not. So go ahead and throw them in here because they don't exist. And then throw them into the stack. So again, the ordering technically doesn't matter. In the test, do it alphabetical. Okay, I am going to go ahead and bring this output somewhere else because it keeps sliding the thing up when I use it. So maybe there. Won't yell at me. Yeah, there we go. Okay. All right. So actually, oh no, it's gonna. Yeah. See, I knew that was gonna happen. Let's just let's put it there. Okay, and then we'll just kind of overflow into the next line. Okay. There we go. All right. So let's go ahead and take out the next thing that we see in our stack, right? So the next thing that we see is the H. Has that been visited? No, it has not. So let's go ahead and put it to our output. Mark it as visited. Add all neighboring nodes, right? Adjacent nodes. What is it? H. So we have 2, G and E. Neither of them are visited. In fact, E is brand new. So let's just throw in G and E. Okay, moving on. I'm trying to pick up the pace now. Take out A. A visited. No, it has not. Mark it as visited. Add it to the output. Put adjacent nodes in there. Why did we just get to A? No, something's wrong here. Yeah, I know what I did there. I took it from the bottom. Ooh, that was risky. I almost failed. Yeah, take out from the top because it's a stack. So take out from the top. All right, so take out the E. Has E been visited? No, it has not. Add it to the output. Add adjacent nodes to the stack that are not visited. So we got C and H. Neither of them are visited, so we are going to throw them in. All right. Okay. Oh, wait. H has already been visited, so we don't need to add it in. So just C, right? Okay. Next comes out the C. Has he been visited? No, it has not. Mark as visited. Add to the output. So I'm going to just put it down here so it overflows into the next line. And then we'll kind of move it later. In fact, That's really annoying how the thing moves. Jeez. All right, stay there. Stay. All right. Okay. So we marked as visited. Now we got to add all neighbors of C that are not visited. So in this case, S is visited. D, E, and F. E is visited already. So we don't need to add that. So I think we just need to add D and F. And D is not present here right now, so we will add it in as well. Okay? So we're good there. Next one's going to be the F. So F is going to be marked as visited and added to the output. And then add them in. So we got C and G. So C and G. C is visited, G is not visited. So we are going to go ahead and add, oh wait, no, G is visited actually already. I just saw it at the beginning there. So they're both visited, so we don't need to add anything. Great. Let's take out D now. Has D been visited? No, it has not. Cool. So we can add it to the visited. We can add it to the output. Neighbors of D. So D only has the adjacent C, which we marked as visited, so nothing needs to be added to our stack. It's good. Our stack's starting to get empty now. It's getting pretty big. All right, G. G has already been visited, so we don't need to do anything to that. We just discard it. F. F is already marked as visited, so we also just discard it. C. C has been marked as visited, so we also discard it. Finally, we get A, but A is not visited, so then we mark it as visited, we add it to the output, and then we have to add all adjacent vertices to A, which are S and B. S is already visited, so we don't need to add that, but B is not even here, so we have to add that there. It's not visited, so we definitely need to add it to the stack. Okay, next we pop out the next thing, which happens to be the B we just added. So we're going to mark that as visited because we've never visited before. Add it to the output. Adjacent nodes. The only adjacent one is A, which is marked as visited, so we don't need to add it. And then we are done with that one. We try to pop from the stack again, but the stack is empty. We don't segfault because we're careful in our code. So instead, we know that we have successfully completed the depth first search traversal. Let's see what this looked like. So it basically went from S to G, from G to E, from E to, or I said E, S to G, G to H, H to E, E to C, from C it went to F, from F it went to D. So what happened here was the algorithm tried probably to go to G, but of course that was already there, so it went back. And then from here, it went back to C. And then from C, it went to D. From D, it went back to C. And then it basically went back all the way to the beginning. So it probably went back all the way up here. And then it finally went this way and then this way. So we probably never ever touched this or that. Okay, but that's fine. So that's a lot. It's a lot easier when you're not trying to talk and do the algorithm at the same time. So don't feel bad. Okay? So any questions about those two algorithms, which you are indeed expected to do on the test? So be prepared. Maybe not both, maybe one. We'll see. Okay. All right, moving on then. One more algorithm for the day, and that is topological sort. So topological sort is an algorithm that is aimed at directed graphs. Are these algorithms more efficient than using the traverse functions? Well, they do different things. For the breadth first search, then yes, doing the level order traversal on the assignment would have been a lot easier to do using the queue. In fact, if you didn't use a queue, I'm actually curious to see what you did. So it'd be interesting to see what happened with that. But yes, you the way you do level order usually you use queues. As for the other one, I mean, when you're doing something recursively, you're inherently using a stack. So you're kind of using the same algorithm that we just did. You're just not actually using a stack. You're using recursion. But you could modify your traversals, like your pre-order traversal, to use a stack instead of using recursion and make it iterative, which would gain you efficiency for a computer versus like overhead of function calls and whatnot. So there's that. Okay, so topological sort. So topological sort is an algorithm that only applies for directed graphs, okay? So whereas these traversals apply for directed and undirected, topological only applies for directed graphs. And in simple terms, let me just start out by showing you the algorithm and what it does, okay? In a way, it's kind of like another traversal per se. You can think of it that way. But interestingly enough, it's a way to also figure out if a graph has cycles in it or not. Okay? If a graph has a cycle in it, then your topological sort is not going to include all of the vertices that exist. So that's one usage of topological sort. So let's go ahead and refresh what the in degree and out degree of a vertex represent. So remember that in degree are the number of edges that are coming into a vertex. So for example, in this case, we have two vertices that are connected to C and that are going towards, that are connected to B and are going towards B. E, on the other hand, has basically three vertices that are coming in, like three edges, basically. And it has one edge coming out, going to vertex S, right? So the out degree of E is 1 and the in degree is 3, okay? So just remember that terminology. Now, this algorithm is very, very easy to do with just a graph that you just feed it in like this. If I want to do topological sort, what I want to do is I want to print out the vertices. So it's going to be an output. The word sort is misleading because it's traversal. So our end game is just going to be a bunch of letters that are the output. And what you do, in fact, here let me copy the graph twice. There we go. So what you do is you first list out all of the vertices that currently have an in degree of 0. In fact, I'll correct myself. You will list out one vertex that has an in degree of 0. And when you do that, then you are going to reevaluate the situation actually. So in this case, I could list out A, I could list out G, and I think that's it. Because all the other vertex in this graph have an edge coming into them. B has an edge, C has an edge, D, F, E, S, T, and N, right? They all have edges coming into them, but G and A do not. So what I'm going to do is I'm going to pick one of them. So in this case, I'm just going to go alphabetical and I'm going to pick A. When you do that though, what you do is you erase all of the edges that are going out of the vertex that you picked. So all the out degree ones. You also make sure that you mark that as done because you already added it to the output. Now you reevaluate the situation, and again you're going to pick the vertex that has 0 in degree. Now G still has 0 in degree, true. But there's also a new vertex that has a 0 in degree now, C. C has nothing coming into it now because we erased the edge, because we kind of janked out A and all its outgoing edges. So let's go ahead and pick C then, just to show you that you don't have to pick G first. So you're going to add C to your output, and again, you're going to erase all of the edges that are coming out of it. Okay? One more actually. This one. Same thing again. So rinse and repeat. So now we got G, B, and D. They're all possibilities. And by the way, the fact that we have multiple choices here show you that just like the other two, topological sort can have more than one answer. Because if I pick B here, then that's going to be part of my answer. But if I pick D, then D is going to go before B. So Just remember that. Multiple possibilities. Again, go with an alphabetical solution in the test to make the life easy for TA. All right, but I'm going to pick B there, which means that I'm going to mark B as complete or visited, and I'm going to erase all the outgoing edges, which is just 1. So now I have 2 choices. I have D and G. All the other ones are taken. So again, I'm kind of going alphabetical. So I'm going to pick D. And then get rid of all of the edges going out of D. Okay? So that actually opened up one more letter. That opened up F. So we got F and G. So I'm going to pick F because that goes first alphabetically. Just again, arbitrarily, I'm making that choice. That's not part of the algorithm. Get rid of that. All right, we got G and T. So G goes first. So this time we're going to pick G. And get rid of that edge. So now we got 2 edges. We got E and T. So I'm going to pick E because alphabetically again. Picking that alphabetical stuff first. And mark that. And then now we got T, S, and N. Here we only have one choice though. We only have one choice, and that choice is to choose T. Because S has something coming in, and N has something coming in. So mark that. Erase that. Yet again, we only have one choice right now, which is S. So go ahead and mark that. And now we have only one node left with no in degree, N. And there we go. That's it. That's your traversal. Okay? One more quick example. That one. All right. So we got A, B, D, C, and E. So we're going to go kind of quicker on this one. So we start with A. So that gets rid of this edge. And then from there, what do we do? Well, they all have edges coming into them. So that means that when our topological sort cannot find any more edges, any more vertices that have no edges coming in, that means that, and there's still vertices to print out, which there clearly are, then that is a sign that there is a cycle in our graph, and that cycle is made up by the remaining vertices. In fact, if any of these vertices were not part of that cycle, then we would have been able to print them out. So you have a cycle. Congratulations, I suppose. All right. So that's a good usage of that. Detecting cycles is something that can come in useful. All right. One last thing that I want to mention is how would you do this, like from like an actual adjacency matrix? And it's very easy actually. If you have a graph, so here I'm going to just put a little simple graph here. So A, B, C, and D. All right, so let's do that one. So let's look at what the adjacency matrix would look like for this. Again, the temptation to make things vertical is too high, but I think if we make them horizontal, we can increase the size. Okay, there we go. So that's just something that I will learn with time, I suppose. I say this in November. All right. So again, we have our from and our to. And by the way, you could flip that, but it's just a choice. I like to do the verticals as the from. All right. So let's create the adjacency matrix first. So in this case, A is going to be. Oh wait, one more line there. There we go. So A is going to B and is going to C, and we also got B has nothing coming in. Well, here let's do the reflection. So 1, 1, 1, 1. And then B has nothing going out, so all zeros. C has nothing coming out, so all zeros. And D has 1 going to C, and then the other 2 are zeros, okay? So that is our adjacency matrix, okay? So if you're trying to pick if you're trying to pick a vertex to choose to kind of remove from the graph to do your topological sort, you look, in this case, because we have the 2 going horizontally and the from vertically, you're going to look at the vertical rows. So you look at these rows, okay? And you're going to look for the ones that have all zeros with the exception of the going to yourself. In fact, for now, I want you to just ignore the diagonal here. So when you're looking at it in the vertical view, you want to grab the ones that have zeros. If they all have zeros vertically like this, then it means that they have no incoming edges. So as you can see, we have 2 choices. We have A and D, okay? So I'm going to go ahead and I'm going to pick A. All right, so when you pick A, that's the same thing as selecting A here. Now you have to worry about removing the edges that are going to other vertices. For that, you look at the horizontal row. So you look at this one. Because you picked A, you look at here, and you're going to swap those letters horizontally. Anything in that row, you're going to swap to 0. So that's going to go to 0, and that's going to go to 0. Okay? After you do that, then you go ahead and revalue it vertically to choose your next one. So that was basically the equivalent of getting rid of these 2 edges. Okay? From there, you will see that B contains nothing. Now, B has all zeros, basically, because again, we ignore that diagonal. And C is not ready yet because there's actually a 1 here, so that's not good to go. And D has all zeros, so you can pick one of the 2. So let's say that we pick B. Okay, so you pick B, so that's added to your output. So now we have AB as our output. And then again, because you remove that, you want to go horizontally and remove any zeros that you see here. Remove any ones that you see there. But as you can see, there's nothing to remove, so you're good to go. Next, you go back for the verticals and find the next one that you can get rid of. This 1 is still here, so you can't pick C, but it's all zeros here, so you can pick D. So you add that to your output, and then go horizontally through that row of D and remove any ones that you see. As you can see, we have 1 there. Let's pick another color, actually. Orange. As you can see, we have a 1 right there. So we're going to mark that into a 0. From there, you go on. And in this case, we only have 1 more letter left. And fortunately, it has all zeros now. That does mean that it is okay to mark as removed. And then technically, you go to the horizontal of that as well. But, there's nothing to change. And you can say you're done. Okay? So, very colorful graph right there. It's quite trivial to implement topological sort when you have an adjacency matrix. When you have an adjacency list, it's not as fun. So just make an adjacency matrix and solve your life. Make your life simple. Just remember 1 method. Okay? But for this one, on the test, I will just make you do the version on top when you do the drawing, because we don't have time to make you do all these algorithms. So I'm already telling you, as long as you can show this version where I remove the arrows and show the output, you're good. This is just for your benefit if you ever need to code this. Okay? So that's it. We actually got through all 3 algorithms with 6 minutes to spare. So, yep, that's the class for you. Any questions? Like I said, next time we're going to be looking at minimum spanning trees. And then the class after that, we're going to be looking at Dijkstra's shortest path. And then we're done. We have that review day, and then that's it. I did forget to record locally, so I am going to have to download the stream from YouTube, or sorry, from Twitch to upload to YouTube. I just noticed that. But that's okay. Hopefully the stream didn't cut off, because nobody said anything if it did, so yeah. Okay then. Well, if there are no more questions, then I will end the stream. So there is that. The last day to redeem attendance is going to be on Monday, November 29th. However, if you already got enough points, redeem it now. So it's only if you think you're not there yet, but you think you'll get there by the 29th. What I don't want to happen is like someone does not come on the 29th and then say like, oh, how do I redeem now? Because you can't. You can only redeem when I'm live. So plan ahead if you're not going to be here on like 29th or something. All right then. If there are no more questions, then that is the end of the class. So I wish you all to have a good weekend, and I'll see you back here on Monday so that we can get some more cool graphing algorithms down. And make sure you get all your assignments done. There's no more extensions now because we're in the end game now. We're at the end of the semester, and the TA needs time to grade. So all the deadlines are fixed now. So get going so you don't have to do extra work on Thanksgiving. Okay. Bye, everyone. Take care. See you next time.